Bismillahirrahmanirrahim. All right, class. Assalamu alaikum and welcome to the first lecture of week 11. So before moving on to the next topics, I would like to briefly fulfill my promise, which I told in the last lecture but forgot to cover, that while moving this d by dt, which is a normal derivative, inside the integral sign, we said that we are doing a Bimani, and actually we are converting this normal derivative into a partial derivative. And why we are doing so? Because if you can see here, or rather if you could see here, the instant when we introduced or injected charges within this volume, definitely, let's say this is the point where we introduced some charges. So the volume charge density would be function of not only time but also space, because at the very edges of this volume which we had considered, the charge density would be minimum at time t equals to 0, the time when we injected the charge, and that would be maximum somewhere in the middle where we actually injected the charge. So after injection, the charges will repel each other, so charge density will also depend on time for the time t greater than 0. So in general, we can say that for this particular example, the charge density is not only the function of position, but it is also a function of time as well. So for this particular case, for which we derive this result, equation number 3, using this procedure, what we got is this. And for this particular example, rho v is a function of position as well as time. So when we were considering this expression, consider the right hand side term, this rho v is a function of x, y and z. Not only that, but it is also a function of time. So after integrating this rho v with respect to volume, and there must be some limits for x, y and z, and after integrating those after integrating rho v and putting those limits, the result of this integral would only be the function of time, because you have integrated this rho v with respect to space x, y, z already, and you have already put the limits, so x, y, z are gone now after integration. So only thing which is remaining is time. So or the only function which will be the resultant after integration will be the function of time. So derivative of time, this is a normal derivative, it makes sense. But if we move this derivative sign within this integral sign, now up till now, since the integration has not been performed with respect to volume or the space, up till now this rho v is a function of x, y and z and also t, because integration has not been performed so far. So now this derivative with respect to time should become partial derivative while we are taking it inside the integral sign. So earlier, after integration, x, y, z would be gone, and only function which will be resultant after this integration will be a function of time. So normal derivative would do the job, but as soon as you move it inside before integration, you must change this normal derivative to partial derivative. Why? Because since integration has not been performed, this rho v is a function of x, y and z as well as t in general. All right, so this was the reason why we considered why we changed normal derivative to partial derivatives. All right, so before leaving, finally I would like to summarize what we have discussed so far, or I want to give you the take-home message. Consider this to be a perfect conductor which is going into the board. All right, so perhaps this is the z-axis and this is the cross section of the conductor, and let's say positive charges are going into this whiteboard, and let's say those positive charges are symmetrically distributed throughout this volume, throughout this cross section. Okay, and they are going into the into the board, or the charges are flowing along the conductor. So for this expression tells us, and let's say the charges are moving with certain velocity v in a particular direction, so direction is considered here, and as I said that there is some concentration of charges around across the whole cross section and also along the whole volume, and let's say that density is rho v. If we take the product of these two entities, what we'll get current density. Now this is charge and this is movement, so charge density and movement combined together gives us something which should be current, because whenever there is a sense of movement with charge, there is current. But since we are not considering charge, rather we are considering charge density and velocity, so we are getting current density. All right, so it gives us the rate with which the charge density is moving along, the current, or the rate with which the charges are moving in a particular direction, the direction of charges per unit area. Okay, all right, if we consider, again this is a conductor, okay, going into the board, if we consider a reference plane which is exactly this board, this white board, or the cross-sectional plane which has been shown here, in this particular case current I will be equals to the magnitude of this J divided by the surface area S. And current is always a macroscopic quantity, remember that. That's why we are getting current by integrating something. Integrating something means this integrand is defined over a very small area, so small that that area can be considered to be a point. So in essence, that equation, the integrand in equation 1 asks us to divide this cross-sectional area into differential surfaces, okay, where each surface is so small that it can be treated as a point, very small, and this J dot ds gives us the differential amount of current, which this J dot ds gives us the differential amount of current which is passing through any differential surface area. What if this surface area is not as shown in this figure, rather if it is tilted like this, the whole surface area? In that case, this J dot ds will have to consider the angle between these two things, and definitely there will be cos of angle between these two entities, and we'll have a value or differential of a value of differential current which will be smaller than the case when we have the case which we have shown here. So integrate all these differential currents together to get the macroscopic current over a certain cross-sectional area. Okay, so remember, this tells us that current is something which depends on the cross-sectional area, or the not cross-sectional area, but the reference plane and its orientation, apart from the direction of motion of charges. Okay, so it's not like this that current is always in the direction of flow of the charges. No, current density is always in the direction of flow of the charges. All right, secondly, this is this case which we had considered earlier and just now. We have assumed that charge density is constant throughout this cross section. In AC case, for example, this is obviously DC. In AC case, alternating current, where there is some frequency, the charge distribution does not remain the same. Rather, the charge, or the current distribution, I should say, the current distribution changes, and it gets concentrated on the surface of the conductor, and in the middle the charge density becomes very small, and as you increase the frequency, the availability of charges, or in other words, the charge density at the center reduces. In this case, how would we define current density? How would we define current density? In this case, we should consider charge density at each point. Let this each differential surface is so small that it can be treated as a point. So we will have to consider each point and consider charge density at that point, and also will have to multiply the velocity with which that charge density is moving. Then the product of these two entities will give us, charge density at this particular point. So similarly, for some other differential area, if we multiply the charge density at this point by the velocity with which it is moving, so we'll get the charge density at this, the current density at this point, the current density at this point, the current density at this point, and all those points, differential points. So it means that this current density is something which is defined at a point, So it is a microscopic entity which is defined at a point, just like charge density. Charge density is defined at a point. At every point, the charge density is different. For AC case, where there is some frequency, the charge density at the middle of the conductor is almost zero, while it is concentrated or very high on the edges of the conductor for high frequency cases. All right. So this J, always remember, this J is always defined at a point. So is rho v. So is the velocity with which that rho v is moving. So J in essence is a differential entity, and it is always defined at a point. What is J which is defined at a point? It is current density. So current density is always defined at a point, and it can be given just like electric field intensity is given, just like flux density is given in the form of some mathematical expression, vector expression, over which if you replace the x, y, z values, you will get the value of current density. But this current is not defined. It's a macroscopic quantity. It's not necessary that it is always defined at a point. It can be defined over a macroscopic, visible to naked eye entity over a big cross section, perhaps in the diameters of several centimeters. All right, so this is always a point concept, current density, and current is normally a macroscopic concept. So current density depends on the direction of the charges and the charge density. So if I tilt the area of the observation plane like this, current would change, but current density throughout this cross section will not change, because that J is not defined over a surface, rather it is defined at each and every point across this cross section or within the whole volume of the conductor. So this is a must take home message. Okay, so higher the charge density, the higher the current density. Or if the charge density is constant, if we have, let's say, 4 microcoulombs per meter cube, but you increase the velocity with which that charge density is moving, current density will be increased. So this is something which we should always remember. Okay, all right, so it may well be possible that, all right, so the current is in relation to the observation plane, while the current density is always in relation to the charge density and the velocity. So the basic entity is current density, not current. Okay, so based on surface of observation or area of observation, current will change, but current density will never change. All right, so this is something which I want to emphasize here. All right, so Let's discuss metallic conductors after discussing the current and current density. Definitely, the material in which current or convection current flows is known as conductors. So before analyzing electrical properties of different materials, let me just give you the some background which you are already aware of. You're already aware of those, but I'm just giving you the major key points which which will give you a quick refresher of what you have already seen in your maybe in your physics courses. All right, so we know that atom that every material is made up of atoms or molecules. If it is an element, so the fundamental entity is an atom for that material. The entity which is the constituent of that particular element, that fundamental entity, or the smallest particle which is related to that particular element as atom. And definitely atom can be divided into several atomic particles like electrons, protons, and so on. So, and for compounds, the fundamental entity, collection of which makes that compound, is a molecule, all right, made up of more than one atom. So this is not the physics or chemistry class, so I'm not going to give you the whole picture of what an atom is and how it is modeled, but the key points. So the atoms are based on Bohr's atomic model. Now that model has been refined several times, and now is accommodating many new facts which were not actually provided by Bohr's, which were incorporated in this model after several other works done by several other scientists like de Broglie, like Pauli's exclusion principle has been incorporated, and several other like Schrodinger's work to model to model the electrons behavior in the field of a crystal structure. So these are the things which were incorporated in the basic Bohr's model, and today we are going to discuss just the fundamental key things which are related to electromagnetics. We cannot dive into the details of how the atom is modeled exactly. So Bohr's atomic model, which was the first model which provided the quantum mechanical foundations for the modeling of an atom, is the Bohr's atomic model. So that model is actually based on in turn Rutherford's model, but with some modifications. So this model basically says that we are not discussing Bohr's model, we are discussing the model which has been accepted now widely. So it says that at the center is a positively charged nucleus, which is made up of protons and neutrons, neutrons being slightly heavier than protons, and surrounding this densely populated, positively charged nucleus are the clouds of electrons, negatively charged electrons. So there are shells like K shell, L shell, M shells, and each shell is made up of several subshells. You must have remembered the S, P, D, F, G subshells, and so on and so forth. So we are not interested in everything which is given by the quantum mechanical model of an atom. What we are interested in is the fact that with each band, or with each orbit, is associated certain energy, all right, and that energy which is associated with each atom with each orbit is actually the energy of the electron which is orbiting in that electron cloud, or which is orbiting, which is present within this this orbit. So the if an electron is present in this orbit and is somewhere in this cloud, it has got certain energy, and as soon as it acquires energy from external sources, it will jump to the next energy. All right, so in between these two energy levels, this is the forbidden region. Okay, electron cannot exist in between two orbits. All right, electron cannot exist here. Either it would exist here or here or here. So there are discrete levels of energies which an electron can acquire, and according to that energy, it will orbit in a certain shell or certain orbit. Okay, orbit, shell, energy band, all terminologies are used interchangeably. Okay, so normally the innermost orbit is the one which has got the most negative energy associated with it, and as you go on the higher orbit, the energy associated with this orbit would be negative but lesser than this one. And if you will go on the next level, the energy associated with electrons in this orbit will be smaller than this one, but it will be negative. So the energy associated with an electron in any of the orbit is the combination of potential energy and the kinetic energy. All right, so we should remember this. And as soon as there is these energy levels, negative energy levels, are defined with respect to another level, another orbit which is infinitely away, infinitely far with respect to the nucleus. All right, so the orbit at the radius r equals to infinity has got the energy 0. So if an electron is over there at that infinity orbit, the energy of the electron will be 0. So since we know that in order for an electron to jump from lower stages to higher states, from lower states to higher states, the surrounding should give energy in form of heat, in form of optical energy. So after absorbing energy from surrounding, electron jumps to the next stages, and since the infinity state is at 0 energy, so definitely these energies which are associated with each of the shells or each of the bands, the value should be negative, because after getting energy, electron is moving towards 0. So it means before getting energy, it was at some negative value of energy. All right, and we know that at absolute 0, that is at the temperature of 0 Kelvin, the number of electrons surrounding an atom is equals to the number of protons in the nucleus. So for instance, if a nucleus has got 11 protons, so 11 electrons will be surrounding, occupying, revolving, orbiting around this nucleus at temperature T equals to 0 kelvins. So, but normally this temperature is not achievable at room temperature, meaning at 300 K. So thermal energy is, for some materials, is so much that electrons orbiting an atom absorbs that energy, and they go and jump to the next states, and then this spontaneously settles back, releasing energy. So you all know these things. I'm just giving you a refresher. So Bohr's atomic model says that energy absorbed by an electron to jump from lower states to higher states should be in form of discrete energies, or which is termed as quanta. All right, quanta of energy is absorbed by electron to jump from lower states to higher states, and when an electron settles back to the lower state, it releases the same quanta of energy. So energy should be conserved. All right, so we are not interested in all the energy bands as long as we are studying electrical properties or electronic properties of materials. Rather, we are interested in energies of the outermost shell, which is known as, or outermost band, which is known as valence band. We all know that. So this band has got the least energy associated with it. Slight absorption of energy by the atom or by the electron can set the electrons in the valence band to jump to the band in which, if electron jumps, it will be free from the influence of this parent atom. So that band is known as conduction band. All right, so if let's say this is energy, so let's say this line shows the highest energy, or the energy which is associated with the valence band. So I'm writing it valence band. Okay, so this is the peak energy, maximum energy which can be achieved by an electron while it is still in valence band. All right, so if a material is such that the edge of the valence band and the edge of the conduction band, in which if electron reaches, it will be free of the influence of the parent atom. If there is a huge difference between this and this energy, it means that electron needs a lot of energy to break away from its parent atom and go into the conduction band. If that is the case, then this material is known as insulator. This region, by the way, in which electron cannot exist, because it must absorb quanta of energy, a discrete amount of energy, to jump between the bands. This is known as forbidden region. Forbidden region. Okay, if forbidden region is very large, then the material is insulator, meaning that for electrons in the valence band, they require a lot of energy to break away from their parent atoms and go freely in the crystal lattice structure, move around, roam around freely. All right, so those electrons which are roaming around freely are said to be in conduction band. Okay, so for insulators, this forbidden region is very large. However, if I draw the same energy band diagram or band diagram for conductors, so you would see that there is actually no distinction between the edges of valence band and conduction bands. So actually in metals or conductors, they overlap sometimes, or mostly they overlap. So there is no boundary between valence band and conduction band. So at T is equals to 0, in the case of conductors, at T equals to 0, at absolute 0 temperatures, all the electrons are settled within their respective orbits. But as soon as you start increasing the temperature and well below the freezing point of water, good conductors, the electrons in the valence band of the good conductors acquire energy from thermal energy from the surroundings, and they start to jump to the conduction band. So forbidden region is not there in the case of conductors or metallic conductors. Okay. Then there is a third type of material known as semiconductors. Semiconductors are generally, a middle arrangement between insulators and metallic conductors. So valence band and conduction band, they are separated by forbidden region, which is comparatively small, very small as compared to the forbidden region of insulators, but this energy is considerable. So intrinsic semiconductors like silicon, germanium, they behave as if they are insulators. All right, not very good insulators, but they are insulators intrinsically. Intrinsically means the way they are found in nature. Okay, but after some modification to their structure, crystalline structure, which is done by doping, these semiconductors, these insulators, these semiconductors which were otherwise insulators, these semiconductors can be converted to behave as conductors. So that's why they are called semiconductors. So let's consider this copper material, which is made up of several copper atoms. Now this is arranged in a crystal lattice structure. So there are, as compared to a single atom, which is rarely possible in nature, in crystalline structure there are several energy bands as compared to a lone atom, which is normally not possible to get. Anyway, let's consider this copper structure, and I've shown E's here. Every E represents a free electron. I am not showing those electrons which are bound to their parent atoms. I am just showing the free electrons. So we have just seen that good conductors are the conductors whose crystalline structure or chemical properties are such that as soon as you are above the 0 Kelvin temperature, they absorb energy in the form of thermal energy from the surroundings, and their valence electrons, they quickly jump into the conduction band and becomes free for conduction. That's why they are called conductors. By the way, insulators can also acquire energy. If it is well possible that insulators acquire energy from the surrounding, from some electric field from the surroundings, and that energy is so much that the valence electrons in the insulators, they jumps and they crosses the potential barrier or the forbidden region, and they jump to the conduction band. If it happens, we say that insulator jal gaya. We say that insulator breakdown has occurred. So in that case, insulator will behave as a conductor. So anyway, now if this is the case, so we know that the number in a neutral material, the number of protons in nucleus is same as the number of electrons in the materials. The number of electrons, by number of electrons I mean those which are bound to their parent atoms, still in their orbits, and those plus those who are free. So combine those number, you'll get the same amount of protons which will be present within the nucleus. All right, so since there are free electrons and positive charges, so the net arrangement is such that the electrons are moving randomly. They are moving randomly just to cancel out any net electric field which is produced by these negative atoms, these negative electrons, and positive protons within the nucleus. So yaqinan protons पॉजिटिव चार्जेस हैं, इलेक्ट्रॉन्स नेगेटिव चार्जेस हैं, इनकी कोई फील्ड बनेगी, पॉइंट चार्जेस हैं ये. तो फ्री इलेक्ट्रॉन्स कुछ इस तरह से मूव करते हैं कि अंदर की कंडक्टर के अंदर की इलेक्ट्रिक फील्ड जीरो हो जाए. So they normally move in a random fashion, these electrons, just to cancel out the total electric field and make it to be zero. If that would not have been the case, if you touch any conductor, you know, which is lying on your table, you will feel shock. But this does not happen. Why? Because the net electric field is zero. So now, if since net electric field is zero, so the force experienced by each of the negative charge or positive charge, whether they are inside in a nucleus or whether electrons which are revolving in their orbit or the free electrons, since electric field is zero, so the force experienced by each of the charge would be zero, since net electric field is zero in a normal conductor. But as soon as so consider this as a conductor, all right? I am showing a portion of it. As soon as I apply potential, positive terminal of battery here, negative terminal of battery here, an electric field will be established. Now this electric field cannot be counteracted by any these electrons, because this is the electrons have already balanced out the effect electric field due to positive charges. But now this is external field which we have applied, so electrons will not be able to cancel out this field. So what they will do, they will experience now some force, and that force can be given as, if I talk about one electron, so that force experienced by one electron after applying this electric field intensity will be charge on that electron multiplied by the electric field. And since we know that the charge on an electron is negative, 1.609 exponent minus 19 coulombs, I guess, if I remember correctly. So this amount of force will be experienced by the electron. So this shows that the force experienced by the electron will be opposite, the direction of force experienced by the electron will be opposite to that of the field itself. Okay, so now what will happen? Now this electron will start to accelerate towards, in this picture, if you consider this arrangement, each electron will start to accelerate from right to left towards positive terminal. All right, had these electrons been in vacuum, these electrons would have accelerated until they reach the positive terminal or until they reach the sink. But there is crystal structure. These are the solid copper molecules, copper atoms, which are, you know, bound together by strong atomic forces. So what will happen? These electrons which will accelerate towards left, they will, you know, hit the thermally excited, you know, these nuclei, okay? Because, you know, as soon as the temperature is not 0 Kelvin, the energy absorbed by a material is used to, you know, break valence electrons away into the conduction band, and the nucleus, it also starts to vibrate. So a solid, especially the conductors, may seem, you know, pretty calm and quiet to you at macroscopic level, but if you go at the microscopic level, at the atomic level, you'll see that due to non-zero Kelvin temperature, the energy, the thermal energy acquired by the crystal structure or the crystal lattice makes the nuclei to vibrate about some mean position. So at non-zero, at room temperature, these all of these nuclei, all of this nucleus are vibrating. All right, all of these nuclei are vibrating about some mean position. So electron, there is a high probability that electron will hit this nuclei. Had there been no vibrations, there will be lesser probability of electron getting hit by, or a nucleus getting hit by an electron. But since there is non-zero temperature, So vibrations are there, so probability will increase. If we increase temperature further, the oscillations will be of even greater magnitude. So probability of getting hit by electron will increase by increasing temperature. So as soon as it starts to accelerate, it will acquire some kinetic energy, but as soon as it will hit the crystal structure, it will transfer its energy to the crystal structure, and its kinetic energy will be zero. After some time, after a few nanoseconds or picoseconds, it will start to accelerate again, and it will then hit another nucleus and transfer its energy to the nucleus, and stays still. Then it will start to accelerate and achieve some velocity. So after some time, which will be in picoseconds or microseconds, these electrons, all of these electrons, will acquire some average. We are not talking about instantaneous. Discussing instantaneous velocity of each electron is fruitless. Rather, we should be interested in the average velocity of each electron or all the electrons, which will be there due to application of this external force or external field. So after some time, this process will continue, will keep on. All right, acceleration of the electron, hitting of the electron, losing energy, and velocity becoming zero, then re-accelerating again, then hitting, transfer of energy to the crystal lattice and becoming standstill, then starting again. So this process will continue throughout as long as there is field. But we can say that after some time, at a steady state, the electrons will achieve some average velocity, and we call that velocity drift velocity. Okay, drift velocity. Why drift velocity? Because these electrons are not moving on their own with their own will due to some their own their innate capability. No, they are not moving due to their innate capability. Rather, they are moving due to an external force. So we can say that electrons को घसीटा जा रहा है, electrons अपनी मर्जी से नहीं आ रहे. ठीक है? So we can say that electrons are being drifted towards one side. So that's why we call the velocity which will be attained by electrons after some time, we'll call that velocity drift velocity, which will be directly proportional to, obviously, electric field, magnitude of electric field, and not only that, the direction of drift will be opposite to that of electric field intensity. So now, if we want to remove this proportionality sign, we'll have to introduce a constant, which is mu. Mu is nothing but mobility, and to emphasize that we are talking about mobility of electron, so we'll append an E here. So mobility is an entity which tells us the ease asani, the ease with which an electron can move through material, through the structure of the material, given an external field is applied to it. Okay, so this is the measure of ease with which an electron can move through a crystal structure. So all right, so definitely ease is something which is inherently positive, like distance is positive, there is no negative distance. So this mobility is always a positive quantity. So this gives us the formula for drift velocity in case of metallic conductors. That's it. Now we know that this is the drift velocity. Okay, and in equation number 2, current density is given by charge density multiplied by its velocity. So this velocity in equation 2, we did not name it, but we can for convection current, this is actually the drift velocity, because before applying electric field, there was velocity associated to each of the free electron, but that was random. All right, so that the net electric effect is 0. So actually there was no current or current density, but now we understood that applying electric field gives the electrons some drift velocity, and if we put drift velocity here in equation number 2, equation number 2 gives us J is equals to rho v. Now you can say that the number of electrons in this material is equal to the number of protons, so rho v is 0. Definitely charge density for a neutral material is 0, but electron density is non-zero. That's why I'm not using rho v here, I'm using electron density, rho e here. All right, rho e is the electron volume density or electron charge density multiplied by drift velocity, which is minus mu e into E. So we've got an expression which is now relating electric field intensity and current density. Earlier we related velocity of the charge density with current density. So it is not possible, it's possible, but it is more useful to talk in terms of electric field, not in terms of velocity. All right, because we are electrical engineers, so we'll try to convert everything wherever possible in terms of voltages and currents and electric fields and and current densities and all. So now if you see that mobility generally, if you try to calculate to find out the units, you'll see that it is measured in meter square per volts into second. Mobility of electron, I'm not using electron here because in semiconductor there are holes as well, so mobility of holes will be represented by mu p, but in metallic conductors we only have current due to electrons, so that's why mu e is there, which is measured in this. And this mu e, by the way, is measured experimentally for every material. So in standard electrical engineering handbooks, or there are data available on the internet. There are very reputable websites which are maintaining data for different physical properties of useful materials. So they have also maintained, the values of mobility for various conductors and various semiconductors under different operating conditions. So now if you try to find that what this is, if you see that rho e is measured in the mu e is measured in meter square into volt second, rather, and then this rho e is measured in meter in coulombs per meter cube. So rho e or rho into mu gives us what? It gives us coulombs per volts into second. Coulombs per second is amperes. So coulombs per second is amperes, and we have got volts and we have got meters here. Volt per ampere is ohms. So amperes per volts will be inverse of ohms, which is Siemens. Siemens divided by meter. So what is this? Siemens is a unit of conductance. We all know from circuit theory. Siemens is for conductance. Siemens per meter is for conductivity. Ohms is for resistance. Ohms meter is for resistivity. So it means that product of charge density and mobility of the charge gives us conductivity. Means that this expression here, this is conductivity, which is represented by sigma. So we can say that J is equals to sigma times E, a very important relationship. Again, we've got question number 4, we'll call it, which says that the conductivity of a metallic conductor is given by negative of charge density multiplied by mobility, electron charge density and mobility. So question number 5. So if I just try to elaborate on this, see, this is the property of a material. This is also the property of the materials. किसी मटेरियल कंडक्टर के अंदर रूम टेम्परेचर के ऊपर या किसी पर्टिकुलर टेम्परेचर के ऊपर कितने फ्री इलेक्ट्रॉन्स होंगे, वो उस मटेरियल की प्रॉपर्टी जो उसके मटेरियल के स्ट्रक्चर पर डिपेंड करती है. सो इन इंग्लिश आई वुड, इफ आई वुड जस्ट रिपीट व्हाट आई हैव सेड, दिस इज electron charge density within a material, and this is based on the material itself. For aluminum, this value will be different. For copper, this value will be different. For silver, this value will be different. And this mobility is also a property of a material which is measured experimentally. So these two things have been measured experimentally for different materials. So product of these two multiplied by minus sign will give us conductivity of the material. So definitely if a material has got more free charges and it provides more ease for those free charges to move along the material, definitely the property of that material to conduct electricity, or in other words conductivity, will be larger. All right. So one interesting thing which you should know, that the mobility of electron for the case of aluminum it is 0.0012, and for copper it is 0.0032, approximately the mobility of copper is 2.5 times higher than the mobility of aluminum. But conductivity of copper is not 2.5 times higher as compared to conductivity of aluminum. Rather, it is slightly lesser than twice higher. So it's still the conductivity of copper is higher than conductivity of aluminum, but it is not as much high as the mobility of copper is higher. Mobility of copper is 2.5 times higher than the mobility of aluminum. But the conductivity of copper is slightly less than twice the conductivity of aluminum. It means that aluminum offers way more free carriers, free electrons as compared to copper. But conductivity is the product of the two things. Definitely, अगर मटेरियल में सिर्फ एक ही इलेक्ट्रॉन रहे, कितनी ही मोबिलिटी हो तो करंट कंडक्शन तो कम ही होगी ना. सो द कंडक्टिविटी इज बेस्ड ऑन द टू थिंग्स, एंड डेफिनेटली if you increase temperature of any material, any metallic conductor, if you increase temperature, the operating temperature, the electrons will start to break away. There will be more free electrons. But remember, more free electrons means that more charge density. But remember that the oscillations will also increase. Oscillations are also increase means that now the ease with which electrons could flow through the crystal structure will reduce, and this reduction is actually significant as compared to the increment in the charge density. So with the increase in temperature, operating temperature, actually overall conductivity reduces. So this is another way, this is another reason why we should consider conductivity, not mobility or charge density to to judge or compare different conducting materials. All right, so this J is equals to conductivity, current density is equals to conductivity times electric field intensity, is known as point form of Ohm's law. Why it is so, we'll talk about it later on, inshallah. Assalamu alaikum.